All right, so remember that vowels are produced without a substantial constriction, and this means that the vocal tract is working a lot like a resonating tube, which we've recently learned about. The difference between different vowels is mainly a difference in the shape of that resonating tube, which affects the frequencies of those main resonances. And it turns out that the articulatory dimensions that we're interested in for vowels, tongue height, tongue frontness, and lip rounding, each correspond roughly to a pattern of formant frequencies. For the most part, close vowels with a high tongue position have a lower first formant frequency, a lower F1, than open vowels with the tongue low in the mouth. Front vowels tend to have more space between the first two formants than back vowels, and rounding tends to reduce the frequency of all formants. Remember that the lips are at the open end of the tube. That's a pressure node for all resonances, and when you narrow a tube at a pressure node, you reduce the formant frequencies. And also, to the extent that the lips are protruded forward, they make the tube longer, which also reduces the resonant frequencies. So let's just look at some examples here. This is the vowel E and the vowel A. Now the main difference between these is that E is a close vowel and A is near open. And if we look at the formants here, we notice that that first formant is lower for E than it is for A. Okay. Now what about if we just move back from a close front unrounded vowel to a close back unrounded vowel? That's E to U. And the main difference here is that that second formant starts out quite high, well above 2000 hertz, and then it comes very low when you go to the back. So front vowels have a big gap between these two formants, back vowels less of a gap. And now here's a subtler difference. If we look at U, the close back rounded vowel, and U, the close back unrounded vowel, these are naturally produced, and we notice first formant goes from 284 hertz rounded to 299 unrounded, so higher frequency unrounded, lower rounded. Second formant is much lower in the rounded version than the unrounded version, and the third formant is actually very close. This is from my speech. I don't have that unrounded vowel in my inventory, and it's very difficult when you're producing sounds live to make them exactly the same except for rounding, for example. So I can't guarantee that there wasn't some tongue movement between those articulations, but you do get that overall sense of lower formants in the rounded than in the unrounded version. Okay, and one more thing that we know about vowels is we can have diphthongs. Diphthongs are sounds that move from one to another vowel-like position, and they're naturally acoustically identified by a movement of the formants. So here is an example of I. This is a fairly artificial one, but it's still representative. And you'll notice that those first two formants start in whatever position they start in, and then they transition into another position for the end of the diphthong. So you have I, and this actually has a long E bit at the end, which isn't typical, but that movement is something you will always tend to see in the spectrogram of a diphthong. Now, one other thing to keep in mind, we've looked at some examples here where the formants are really distinctive. It can sometimes be difficult to get computers to automatically measure them, but actually by and large it's not too bad. But there are instances where two formants are so close together that it's difficult for human researchers to distinguish them when reading a spectrum or a spectrogram, and where it can be difficult for the computer to distinguish them. And so here's an example of O, that open O sound, where the first two formants, this was artificially generated, so I happen to know that the first two formants were at 731 hertz and about 977 hertz. So they're still just over 200 hertz apart, but with a fundamental frequency that's often above 100 hertz, that's only two harmonics distant, and we don't see two distinct peaks in the spectrum here. And so me as a phonetician looking at that spectrum, I wouldn't immediately be able to say, yes, there are two formants here. And a computer algorithm that's trying to track these things also would have difficulty with that situation. And just to finish this up, I do want to recommend the Appendix C1 in the textbook has a table that summarizes the results of two key studies that were done many years ago on formant frequencies for different vowels in men, women, and children. And so you can see the sort of patterns we're looking at here played out across a bunch of different vowels. These are American vowels, an American study, but they're the vowels of the IPA, so the patterns hold regardless of the language that you're looking at. So do have a look at that. And next up, we'll be looking at consonants.